Hi, I'm Claire Marie.
And I'm Maheen Javed, and our DSP mini project will be identity-based speech recognition. Speaker verification aims to accept or reject a claimed identity using different techniques such as analysis of speaking rate, phonetic duration, word usage patterns, spectral features, or as we did in our project, frequency durations and contours. It can identify a speaker from a set of known speakers. However, speech is highly variable and can be easily distorted and it's hard to gain 100% accuracy. It can be combined with other techniques such as biometric IDs to provide additional security.
Voice analysis in the time domain would be extremely difficult and impractical. Because of this, we analyzed the speech signals in the frequency domain. We converted the signals in the frequency domain by using discrete Fourier transform. We also discarded frequencies that were greater than 600 Hz because the frequency range of the human voice. The general sampling rate for MATLAB's code recording command that we used is 44 kHz, which meets the Nyquist criterion.
Our voice recording algorithm records 20 voice samples of 2 people, 10 per person, taking 2 samples per second. These samples are then stored in an 88,200 by 20 matrix as our baseline recordings that will have their frequency content averaged to compare with a sample taken in our next script.
This is a flow diagram for our voice rec script. The code first starts by asking person 1 to record their voice 10 times. After person 1 has recorded their voice, the code asks for the second person to record their voice 10 times. The code then asks you to type project in the command window to run the project script.
The recordings are then stored as G1 to G10 for the first person and H1 to H10 for the second person. Using mathematical analysis of the frequency spectra, the standard deviations are calculated for a person 1 and a person 2. An identity is only confirmed only if the recording is within 2 standard deviations of their respective calculated standard deviations.
This is the flow diagram for the project script. Both sets of recordings are cropped and placed in an 88,200 by 20 matrix. The columns are then converted into the frequency domain using the FFT. We then take the modulus of the matrix, normalize the spectra, and place it into a new matrix, then normalize again. We then find the matrix average and standard deviation. Once the standard deviation is found, the project script asks the user to record their voice for comparison. This is cropped and placed into an 88,200 by 20 matrix, converted into the FFT and normalized. We then calculate the average and the standard deviation. If the standard deviation of the second recording falls within the acceptable range of person 1 or person 2's standard deviation, the script will then output who is speaking. If it does not, the script will output that neither of the previously recorded persons are speaking. A graph of the voice recording frequency spectra is also displayed.
One optimization we performed is to use our average vector and our standard deviation to find a lower value of standard deviation that could make our code more accurate for us. We applied the central limit theorem on the 88,200 samples we obtained to perform analysis based on our recording representing a normal population. This assumption is based on the fact that large sample populations can be safely assumed to approximate a normal population. This helps us determine a window of acceptance of how many standard deviations the sample recording can be within. The trade-off is that as we increase the accuracy of successfully identifying person 1 or person 2, we also increase the error of false identification, such as person 1 being identified as person 2 incorrectly. The graph compares person 1's average and the baseline recording's frequency spectra. As you can see in this case, the frequency content of the sample recording on the top lies within 2 sample standard deviations of the baseline recording's frequency content on the bottom. This is the MATLAB screen, so we can enter the project, and I'll enter my name. And I'll record my voice. Maheen. And it'll recognize me as person 1 and generate these graphs. Okay.
So I'm going to do the same thing as Maheen and run project 2. Then type in my name. It'll ask me to record my name. Claire.
enter.
And then it says hello person 2, which I'm person 2. And this is the output of the frequency of my average recordings and my speaking. So we're going to test the program not recognizing either of our names. So we're going to, Maheen and I are going to say our names at the same time. So we're going to run the program. We're just going to write in Maheen's name or my name for... So we're going to say both of our names at the same time.
Maheen.
Claire. And then it recognizes that the person speaking is not me, because it is both me and Maheen. This can be adapted to include as many people as possible. We did conclude that if the number of people were to increase, the level of accuracy would go down. There is a chance that more than one person could fall into the standard deviation range. However, if this were to be made more accurate, it could be used to expand on current voice recognition applications. There are many security, medical, and personal advantages to voice recognition, and accuracy is a key feature in advancing these technologies. We would like to give a special thanks to David Roberts from cnx.org. He originally created a voice recognition script that would tell if one person was speaking. With his code, we were able to expand the code and make it to differentiate between two speakers.